Hello travelers, and welcome to Adventures in Security. In this video, we explore IPsec, how it works, and how we use it to protect information assets. You can download the video script from the link below. Today we're going to unpack IPsec in a way that's practical for networking and security work. We'll start with a clear definition, what IPsec is and the security services it can provide. Then we'll look at the main components. ESP and AH on the data plane, IKEV2 on the control plane, and the idea of a security association, or SA, that ties it all together. After that, we'll get concrete and look at what an IPsec packet looks like on the wire in both transport and tunnel mode. Finally, we'll compare IPsec to TLS, because they're often confused. And we'll close with common use cases like site-to-site and remote access VPNs. Let's dive in. IPsec stands for IP security, and it's best to think of it as a toolbox of standards that protect traffic at the IP layer, Layer 3. Because it operates below TCP and applications, it can secure almost any IP-based protocol, whether that's a web request, a DNS query, or even a ping. Depending on how you configure it, IPsec can encrypt data for confidentiality, add integrity checks to detect tampering, authenticate peers so you know who you're connected to, and prevent replay attacks using sequence numbers. VPNs are the most common mental model, but I want you to keep the bigger idea in mind. IPsec is security for IP packets. Let's locate IPsec in the networking stack. IPsec sits at the network layer, so it wraps or modifies IP packets directly. That gives you a big advantage. Applications usually don't need to be aware of IPsec at all. If the network stack says this traffic must be protected, it happens automatically. Because it's at Layer 3, IPsec can secure different topologies, such as host-to-host between two servers, gateway-to-gateway between two sites, or host-to-gateway for a remote access VPN. This is a nice contrast with TLS, which secures an application session, like a browser talking to a website. IPsec protects traffic between IPsec peers. TLS protects conversations between applications. IPsec has a few core pieces you should memorize. On the data plane, we have two protocols: ESP, which can provide encryption and integrity, and AH, which provides integrity and authentication without encryption. In modern deployments, ESP is by far the most common. On the control plane, IKEV2, Internet Key Exchange version 2, handles key agreement and authentication, and it sets up the security associations, or SAs, that ESP or AH will use. An SA is basically the agreed-upon recipe: algorithms, keys, lifetimes, and counters. Finally, IPsec isn't encrypt everything all the time. A policy engine decides which traffic must be protected, which can pass in the clear, and which should be blocked. Once you see these roles, policy, negotiation, and packet protection, IPsec starts to feel much less mysterious. Here's the concept that unlocks IPsec. The Security Association, or SA, an SA is unidirectional, meaning it describes protection for traffic going in one direction. So for a two-way conversation, you normally have an outbound SA and an inbound SA. Packets reference an SA using an SPI, the Security Parameters Index. In practice, receivers find the right inbound SA by looking at three things: the destination IP address, whether the packet is ESP or AH, and the SPI value inside the IPsec header. The SA then tells the device which algorithms to use, which keys, what the current sequence number is, and how long the SA is valid. Implementations also maintain a security policy database, SPD, for what to protect, and a Security Association Database, SAD, to store the live SAs. Now let's talk about how the keys appear in the first place. IKEv2 is the negotiation protocol that sets up IPsec securely. In the IKE_SA_INIT exchange, the peers agree on cryptographic algorithms and perform a Diffie-Hellman exchange to create shared key material. Then in IKE_AUTH, they prove their identities using a pre-shared key certificates, or EAP, for remote access logins, and they establish the first child SA, which is the SA that ESP will actually use to protect data packets. One thing I want you to remember operationally. SAs are not forever. They have lifetimes. So IKEv2 periodically rekeys by creating new child SAs and switching traffic over cleanly. That's how long-running secure connections can run for days while keys rotate underneath. Now let's connect the packet format to the two modes you'll see in practice. In ESP transport mode, you keep the original IP header for routing. Right after it, you add the ESP header, and then you encrypt the upper layer payload. Think TCP header plus application data, along with the ESP trailer fields. The IP addresses remain visible on the network, but the conversation inside is protected. In ESP tunnel mode, the thing you encrypt is an entire inner IP packet, including its IP header. Then you add a brand new outer IP header, so routers can deliver the packet between the two IPsec gateways. This is why tunnel mode is great for VPNs. It hides internal addressing and protects whole subnets. The trade-off is overhead is bigger, so you have to pay attention to MTU and fragmentation. AH is the other IPsec data plane protocol. The authentication header. AH does not encrypt. Instead, it provides integrity and peer authentication by computing an integrity check value, or ICV, over the packet. The AH header includes a next header field to indicate what comes after AH, a payload length, the SPI, the sequence number for anti-replay, and then the ICV itself. One subtlety is that AH can cover parts of the IP header too, except fields that are expected to change in transit, like TTL. So why is AH uncommon today? Real networks often do NAT, and NAT changes IP addresses and sometimes ports, exactly the kind of changes that can break AH validation. ESP can provide integrity as well, and with fewer deployment headaches, so it's the default choice in most designs. Let's walk through the life of a packet. On the outbound side, the device first checks the security policy database. Is this traffic supposed to be protected? If yes, it selects the outbound SA, inserts ESP or AH headers, encrypts if needed, computes the integrity tag, updates the sequence number, and sends the packet. On the inbound side, the receiver looks at the SPI to find the correct inbound SA, then it performs anti-replay checks using a sliding window so duplicated or old sequence numbers get rejected. Next, it verifies integrity, the tag or ICV, and only after that does it decrypt and hand the original payload up the stack. Notice the order. Verify first, then decrypt, because that's safer. When things break, the usual suspects are mismatched traffic selectors in policy, wrong authentication, or MTU/fragmentation that breaks packets before they're processed. People often ask, if we have TLS, why do we need IPsec? The answer is that they solve different problems at different layers. TLS protects an application session, like a browser to a web server, so it's perfect when you control the app endpoints or can terminate TLS at a proxy. IPsec protects IP traffic between two IPsec peers, which is ideal when you want to secure many applications at once or connect whole networks through a VPN. Identity models differ too. TLS is usually about authenticating a server to a client using certificates, while IPsec authenticates the peers, which might be gateways representing entire networks. NAT and mobility are another difference. TLS is typically NAT-friendly, while IPsec sometimes needs NAT traversal. Often UDP encapsulation on port 4500, and tunnel mode can hide internal addressing, which TLS doesn't do. Let's end with where you'll actually see IPsec. First is the site-to-site VPN. Two networks connect through gateways, and users don't need special software because the gateways handle the tunnel. Second is hybrid cloud. Many organizations build an IPsec tunnel from an on-prem firewall to a cloud VPN gateway, so private subnets can communicate securely. Third is remote access. Your laptop runs an IPsec client and tunnels into the corporate network, often using IKEv2 with EAP, so you can integrate with usernames, certificates, or multi-factor systems. A fourth pattern is east-west protection inside data centers, encrypting traffic between subnets or security zones to reduce lateral movement risk. And because IPsec is standards-based, you can often connect equipment from different vendors as long as the crypto and policies match. That's it for this video. If you learned anything, please remember to give us a thumbs up and subscribe. And until next time, be careful what you click.